Unit 4 is on revolutions in modern physics, so we're basically going to be looking at our development of understanding in the past, say, 2, 3, 400 years or so, some of the significant things that have happened in that time that have allowed us to get a better understanding of the universe and what makes it up and how it operates. You can see the first thing that we're going to look at here is quantum theory. The first dot point there that's highlighted deals with evidence for light being a wave, but before we get into that, I want to just talk a little bit more about light and the models that we can use to describe it. So the first thing to be aware of is that light is energy. We've seen that before. We know that light's energy, lots of different forms of energy, light being one of those. One of the things that is important about energy is that it can be transferred, and there are two models that we're going to have a look at that deal with how light energy can be transferred. So two models for light to describe how it can be transferred. And the crux of quantum theory is basically looking at these two different models. And we'll start off by identifying what they are first. And the first one that sort of fairly prominent in Isaac Newton's time was the particle model. And the particle model basically is just looking at that idea that energy is transferred through the movement of matter. And when we're talking about matter in this case, I'm going to put that in inverted commas. As we go through, you'll see it's difficult to think about light as being matter as such. But there are certain properties of matter that we can refer to that it appears as though light does behave as a particle. And the second one then is the wave model. Now, if you cast your mind back to Unit 2, a wave transfers energy without transferring matter. So ultimately the difference between these two is how energy is being transferred. Particle model, it's with the movement of matter, and with the wave model, it's without the transfer of matter. Now, the word model is an important one to focus on here as well. If you think about some models that you might have seen before, say model cars, model trains, they're a good analogy or a mental picture of something that can be used to explain something else, or a different scenario or a different object. In the models that we're talking about here, we're looking at how particles and waves can be used to explain phenomena that we can observe with light. And as is the case with model cars and model trains, they may represent some aspects of those other phenomena or other objects really well. There are going to be some things that they don't accurately address as well. So keep that in the back of your mind as we go through these ideas. There's a few things that will be explained particularly well by one model, but not well by another. Now, as I mentioned early on in our understanding of light, and so we're going back to the 1600s and 1700s, light was thought to be a particle. And the reason for that was sort of the idea of rays of light that you could sort of identify that there's a light source and there's light projected onto a wall, so there's these rays that are being radiated out by the light source. And that so the particle model was the one that dominated the scientific community, and that's in large part to the work that Newton had done, and he came up with this theory. It was known as the corpuscular theory, and a corpuscle is basically just a particle of light, so hence the name corpuscular theory. And the phenomena that were particularly relevant here were reflection and refraction. And so if you think about an object, say a ball, and you have that bouncing off a wall, then you could identify the reflection of that object bouncing off the wall would be appropriately described by particle motion. Refraction, likewise, if something's moving along and then hits something where it slows down, the path that it travels will vary. And so the corpuscular theory was able to explain reflection and refraction, but it had a particular issue in that there were a few other phenomena that were discovered that it wasn't able to explain. So those phenomena, things that we already saw in Unit 2, the phenomena being diffraction of light, so where it bends around an object or through an opening as it spreads out, polarization, so where you can limit the oscillations of light into one plane, and interference. And it's this aspect of interference that is important when we consider Young's double slit experiment. So moving on to Young's double slit now, this was an experiment that was conducted in 1801. It was a fairly revolutionary experiment and one that still gets referenced today in a few different scenarios. And it was one of the sort of the turning points in convincing the scientific community that light wasn't actually a particle, it was a wave. And so this experiment provided evidence of that particular aspect. So when we're talking about models, we need to see evidence that will support the model, and in this case the evidence was that light can interfere with itself, and therefore that's a property that can be explained by waves but can't be explained by particles. And in order to explain that, we'll just have a look at this setup of this experiment first. So rather than putting this into words, let's look at how it was set up experimentally. Now, the first thing we're going to have over here is a light source. Just representing this as a light bulb, it's the easiest way to think of the light source, but not the same sort of light source that Young would have actually used in his experiment. Then, a bit further away from the light source was a single slit. Now, I need to mention here that this diagram is definitely not to scale. I'm just using it as a good representation of the way that the experiment was set up, but certainly not to scale. We'll actually do an experiment in class to have a look at Young's double slit experiment, and the slits themselves are very closely spaced and very narrow. So that's the setup. The first slit was basically to make sure that light was sort of being produced in a fairly narrow beam. That was then illuminating the double slits, and then the screen was positioned there to observe what could be seen. Now, if we think about the particle model prediction, so we'll start with that first. So this is now looking at if light is consisting of particles that travel in straight lines. The prediction there is that light should travel from the light source, through through the single slit and then over to the screen, or it might travel through the other slit. And note that these don't quite line up, we'll just ignore that. Could travel through the other slit and then produce another band, another bright region on the screen over here. So on the screen what we'd expect to see is a bright region in that vicinity, another bright region in that vicinity, representing where the light travelling through the slits, and then everywhere in between that would have been dark, and everywhere outside of that would likewise always also have been dark. So basically the prediction, keep in mind that these lines that I've drawn here are the prediction of the of what would happen for the particle model, and so the prediction then is that light particles would travel through one of the slits, so travel in straight lines through the slits, and that would then produce two bright bands with a dark region in the middle. And the reason why I'm pointing out the dark band in the middle, it's a fairly significant aspect of what was actually observed, and what was actually observed was something very different. So the actual observation, when this experiment was set up and the light was turned on and the pattern on the screen was observed, was a bright central region. So the particle model predicts that it should be dark in the middle, but what was actually observed was a bright central region, and then alternating dark and light bands either side of that. And I'll just go back to the diagram to explain that in a bit more detail. So instead of seeing this dark region in the middle, what was actually observed was a bright region through the middle here, and then alternating bands of dark and light. So outside of that was a dark region. Again, keep in mind this is just a diagram, so it's not particularly well represented, the pattern that you would see here. But ultimately we're getting this alternating pattern of light and dark, which, when you compare it to the particle model expectation, is very unusual. Instead of just having the two bright bands, we're actually getting this alternating pattern, dark and light, that continues on both ways. And fairly significantly, instead of that dark region through the middle, we've actually got a bright region through the middle. So that's the actual observation. The only way that could be explained, as Young identified, is that light is behaving as a wave. So the ways to interpret those observations are as follows. The first thing to identify is that the light from the double slits consists of coherent light, and when we say coherent, what we mean is that it's has the same frequency. So they're sort of both alternating at the same rate, and it's in phase. And by in phase basically just means it's doing the same thing at the same time. So two peaks travelling through those double slits at the same time, and then two troughs travelling through it at the same time at some later point. So the first thing to identify then is that the bright central region is constructive interference. And the reason why it's constructive interference is that the path that the waves would have to travel to get to that central region is exactly the same length. So if the source of light is coherent and in phase, it means that in the middle we're going to see constructive interference, where peaks are meeting peaks and troughs are meeting troughs, so it's always going to be a bright region. The second point then, if we go to the bright regions outside of that, they are always going to be constructive interference as well. The difference here though is that when you start to move away from that bright central region, the light from one slit has to travel further, and so the difference in those two paths has to always be a multiple of the wavelength of the light. So we're always still going to have troughs meeting troughs and peaks meeting peaks. It's just that it's effectively going to be sort of one wavelength behind from one of the slits, so that they're always still going to be in phase when they reach the screen, and that distance that it has to travel further is always going to be an integer multiple of the wavelength. Now there is a bit of maths that we can put behind that. We're not going to do that here. It's not actually required in this physics course. If you do look up Young's double slit experiment, you'll see that there are a few equations that relate to these bright and dark regions. And we'll have a look at that when we do the prac in class, but we don't need to worry about that level of detail for the understanding of this particular concept. Now the dark regions are basically going to be destructive interference. It's a bit difficult to explain this idea without getting into the maths of it, but basically light from one of the slits is going to travel a greater distance that basically corresponds to a half or 1.5 or 2.5 wavelength difference. And that basically then means, let me just note here, 1.5. further than the other, and so we're always going to have peaks meeting peaks, troughs meeting troughs, and as a result destructive interference. And that means that it's going to then reach the screen out of phase. So the two sources are now doing opposite things at the same time, and so they'll cancel each other out. The conclusion from all of that then is that if you've got a model that can't explain that phenomena and there's another model that can, we can then identify that that second model seems to be a bit more applicable, and so light then behaves as a wave. Those other phenomena of reflection and refraction can also be explained by light behaving as a wave, and so that particular model then started to dominate for the next couple hundred years, until we got to the sort of late 1800s, early 1900s, where we then had another big change in our understanding of light. We'll have a look at some of those concepts moving forwards into the next few videos.